Alright, welcome back to our lecture. Now, this idea of the greenhouse effect, it feels so modern, doesn't it? It just seems like it's the kind of thing that must be a relatively new innovation in science. You'd probably be shocked to know, though, that the whole idea of the greenhouse effect has actually been around since the 1800s. Filled with misunderstandings, though. In fact, that's where the name comes from. Scientists were explaining the greenhouse effect back then in terms of like a greenhouse, like as in where you keep plants in the winter kind of thing. Turns out how greenhouses work has nothing to do with long-wave radiation and short-wave radiation and so on. It has to do with the fact that it is enclosed and it keeps cold air from coming in. But the idea of the greenhouse effect keeping the Earth warmer than it would have been without it, in much the same way the walls of the greenhouse keep the plants warmer than they would be without it, is a lovely idea. And the original formulation of this whole idea came from Svante Arrhenius, an old dead white guy of science from a long, long time ago, who was the first guy to actually come up with the explanation as to how greenhouse gases in the Earth's atmosphere could be doing this. You can understand it was a bit of a challenge when, you know, in the history of science, we figured out that we were really too far from the sun to be as warm as we are. I mean, it took a sizable amount of science to figure this out. And they're just people that came up with this stuff. We should be able to do it too. We should be able to actually come up with some numbers and figure out what the greenhouse effect is doing and how it's doing it. And the tool that scientists do use to figure things like this out and test their knowledge of it is a model. Now, model can mean lots of different things, and we're going to be talking about different kinds of model here, but this is kind of just a little conceptual model that we're going to be building here, where we're just going to be trying to make some simple idea of how the atmosphere could be working, and how just simple ideas about like the transmissivity and the absorptivity could give us a simulation of how the atmosphere is doing it. This is not the same thing as these giant climate models that simulate climate change that we're going to be learning about, especially in the third unit of the course. These are just going to be a simple little thing on a PowerPoint slide, okay, a little conceptual model. In order to make any kind of model, because a model is a simplified version of the real world, you have to make assumptions. And so let's think about the kind of assumptions we're going to make when we make a simple little model of how the atmosphere might be working. For example, well, we learned like really early in this lecture that the atmosphere is not really completely transparent to the Earth's to shortwave radiation from the sun. In fact, gases and aerosols in the atmosphere absorbed about a quarter of the radiation from the sun. But let's make our life simpler for right now and just say the Earth's atmosphere is transparent to visible radiation from the sun. Transparent. That means the transmissivity is 100%. 100% of the radiation that reaches the top of the Earth's atmosphere will go right through the Earth's atmosphere except for whatever's reflected away. Okay, that's going to not make me hugely happy in the sense that I know from like this diagram here that we got from NASA that that's not exactly how it really works, but that's the nature of a model. We're making an approximation here. Okay, let's see how that approximation is going to work. In the same way, we have another approximation we need to make, and this has to do with what's going to be the story of long-wave radiation. We're going to make the assumption that the Earth's atmosphere is opaque to the infrared or long-wave radiation that's being emitted by the surface. Opaque here meaning that like the transmissivity, those wavelengths, the monochromatic transmissivity, is zero. None of that radiation gets through. Well, it mathematically sounds pretty neat. I bet that's going to put some zeros in the equations and stuff like that. But I don't know if I like that assumption all that much. I mean, looking again at this diagram from NASA and our understanding from the previous part of the lecture, we know that that's not right. Okay, we know that the atmosphere is not completely opaque. Some radiation is making it through the Earth's atmosphere, like through the atmospheric window and so on. That's the nature of a model. We're making some approximations. Another assumption that we're going to make that's pretty straightforward is we're going to assume that the Earth's atmosphere and the surface of the Earth are black bodies. That's a term that comes to us from physics that basically means it's emitting radiation purely based on its temperature, not based on the materials that it's made of and so on. That's not such a terrible assumption. Although, again, by looking, for example, at this diagram where we had the transmissivity of the Earth's atmosphere for different gases and so on, it's a little bit beyond the scope of this class to show, but that demonstrates that, in fact, the atmosphere is not exactly a black body. But this is not a physics class in the physics department where they would get all excited about the theory behind that and so on. Okay. Another assumption that we could make is that we may be able to treat the atmosphere like it's made up of layers or slabs. Like this layer of the atmosphere is going to do one thing. Like it's going to emit this, it has one temperature and it's going to emit this much radiation. It's going to absorb this much radiation. And here's another slab of the atmosphere. And we'll say it has some temperature, so it's emitting a certain amount of radiation and so on. This is a common assumption when you're making some kind of model in the Earth's atmosphere, is that it's okay to divide the atmosphere up into little pieces and then just treat each piece like the same thing is happening throughout. Okay, I just wanted to disclose. Now, in practice, of course, you would, as a researcher or a modeler, you'd have to make decisions about like how many layers you want, and is your result that you're getting a function of how many layers there are, and so on. I mean, there's all kinds of theory of modeling type issues here that I don't want to get into. Instead, let's just make this as simple as possible. Let's make our model a one-layer model. We are going to treat the atmosphere like it's one slab of gas. And that slab of gas does something, but the atmosphere, like it emits radiation, or radiation is transmitting through it or something. We're not going to worry about like, oh, but more radiation is being transmitted at these heights, or that more is being absorbed at these heights or something. Let's not go there yet. This is a simple example of what is classically taught in like an atmospheric physics class or a climate physics class called a one-layer model, where you are just describing the atmosphere as this single slab of gas that radiation either moves through or doesn't move through, or it emits radiation at a certain quantity based on its temperature and so on. So, if we assume that this slab, this layer of the atmosphere, is in some kind of energy balance with the Earth around it and so on, and that its temperatures are not changing with respect to time, there's actually a lot of stuff we can do about this. For example, we know that averaged over day and night, averaged over all the latitudes of the Earth and so on, we know that about 340 watts per square meter of shortwave radiation is going to be reaching the top of that slab of atmosphere. And some of that radiation is going to not really play a part in any of this. Some of that radiation is going to just be reflected, either by clouds and get reflected back into space, and that radiation is gone, or get reflected off of the surface of the Earth and be reflected back off, off of snowpack or something like that, and get reflected back out into space and be gone. But some amount of it is going to be passing through. So let's just say 238 watts per square meter of that radiation is actually going to penetrate into the Earth atmosphere system, and let's say because of reflection, 102 watts per square meter gets reflected away. Okay, these are numbers I just picked off of diagrams that we had from that figure off NASA. Okay, just sort of a ballpark thing there. Okay, because we're going to be playing with these numbers later. All right. If 238 watts per square meter is going into the Earth atmosphere system by thermal equilibrium arguments, that means 238 watts per square meter also have to be headed out of the Earth's atmosphere system, which is what I'm indicating there with that red arrow. So 238 watts per square meter of shortwave radiation from the sun got absorbed by something, gas, the surface of the Earth, whatever. Therefore, to be in thermal equilibrium, which we know the Earth is not quite, but we're just thinking right now, 238 watts per square meter have to be headed out of the Earth atmosphere system, being emitted by the atmosphere, or being emitted by the surface of the Earth, or something like that. Well, where is that coming from? Well, we made a great simplifying assumption here along the way. We assumed that the atmosphere was opaque to long-wave radiation, so whatever long-wave radiation the surface of the Earth is emitting, we don't care about that right now. That radiation is absorbed by the atmosphere. It is not what's making it out at the top of that atmosphere. All 238 watts per square meter of that radiation must apparently be emitted by the atmosphere itself. That is radiation that the Earth's atmosphere is emitting in this simple one-layer model. Now, from the point of view of these kind of slab models, the atmosphere doesn't know up from down. It doesn't. When it just radiates it radiates just as much radiation up as down. So if the Earth's atmosphere has to be emitting 238 watts per square meter upward, it apparently has to also be emitting 238 watts per square meter downward. Now, that 238 watts per square meter of shortwave radiation, which I have indicated there with that red box, that is radiation that reached the top of the Earth's atmosphere and is headed on in. But we already said that the Earth's atmosphere is transparent in this model, transparent to shortwave radiation. So all 238 watts per square meter that went into the surface, the top of the atmosphere, is apparently making it to the ground. Okay. Simple little model here that we're putting together. We're going to get way more complicated later. So the surface of the Earth is apparently receiving 238 plus 238 equals 476 watts per square meter of radiation. It's getting 238 watts per square meter of shortwave radiation from the sun, and it's getting 238 watts per square meter of radiation being emitted by, long-wave radiation being emitted by that opaque atmosphere. All right. Well, to be in energy balance then, the surface of the Earth is apparently emitting 476 watts per square meter. So that the net energy balance overall, averaged over 24 hours, averaged over all the latitudes, etc., is apparently also 476. All right. We're putting together this basic model here. So, if we have now determined that for this simple one-layer model, where we made these really grotesque assumptions, like the atmosphere is completely transparent to shortwave radiation, the atmosphere is completely opaque to long-wave radiation, etc. We made all these assumptions here. We figured out by reasoning that the surface of the Earth is apparently emitting 476 watts per square meter in this model. Okay, well, you know what? We've got Stefan-Boltzmann's law. And Stefan-Boltzmann's law tells us that at a certain temperature, you emit a certain amount of long-wave radiation. So we can use it the other way around and say, hey, I know how much radiation I'm emitting, what is my temperature, and you get 303 Kelvin, which is 30 degrees Celsius, which is 86 degrees Fahrenheit, which is actually not a terrible approximation to the real temperature of the Earth. The real temperature of the Earth is average temperature of the Earth is like 68 or something like that Fahrenheit. So, I mean, we're not terribly far off here with a ridiculously simple model. Don't get me wrong, I understand working your way through that derivation, what I just did there, is not such an easy thing, but these had simple in the sense of it had very simple assumptions, like the atmosphere was completely transparent to shortwave radiation and so on. Just for the sake of argument here, I won't go through and make another simple model like this, but we could have where we made a simple model where the atmosphere was not opaque to shortwave radiation. And in that simple model, we would make the same assumptions except for we're changing the opacity, we change the monochromatic transmissivity of the Earth's atmosphere to long-wave radiation, and you get 48 degrees Celsius colder than that, so you get negative 18 Celsius, which is, I don't know, right around 0 Fahrenheit, for the temperature of the Earth. Not a particularly good approximation to what would really be happening in the Earth's atmosphere if we didn't have greenhouse gases, but it gives a sense that we're on the right track here, right? By even making this very crude assumption that, like, the atmosphere was completely opaque to long-wave radiation, we actually got in the ballpark of the right answer. And the real atmosphere is not completely transparent to shortwave radiation. It's not completely opaque to long-wave radiation. The atmosphere is actually made up of lots of layers, not just one layer. Each individual layer has different transmissivities and emissivities and so on, which we will get there. But as a simple little idea here, what we're seeing is that the addition of an atmosphere that is opaque to long-wave radiation, that is to say, contain plenty of greenhouse gases, significantly warmed the surface of the Earth. We ended up with a result that was like 48 degrees Celsius warmer than we would have had without it. The greenhouse gases can be thought of here as making it harder for the surface of the Earth to lose heat to space. And therefore, the only way to get back into radiative balance or energy balance or thermal equilibrium or whatever you want to say is by increasing the temperature of the surface of the Earth enough that now you have enough emission of long-wave radiation that the surface, that it overcomes the resistance of the greenhouse gases to the flow of that radiation. But that's going to be hard to think about, and we've had a really long lecture. I mean, we've taken this ideas of these greenhouse gases. And we've built on the things that you learned in 100 level classes. And we even were able to build a simple one-layer model that was transparent to short-wave long radiation, opaque to long-wave radiation, one temperature for the whole Earth. There's all kinds of places here with room for improvement. That's the nature of modeling. You start with simple models, you build more complicated models. And we shall. But not right now. This has already been a really long lecture. So let's answer a couple quick questions about what we've seen, and then we are done with lecture 2A. Question 12. In our simple model of the Earth-atmosphere system, we assumed that the atmosphere was transparent to blank radiation. Shortwave or long wave? Make a choice from those two options and get some feedback before you move on to question 13.